Good morning, good afternoon, good evening, depending upon where you're connecting from. I'm Ira Feldman. I'm the Managing Director of the TinyML Foundation. And I would like to welcome you to today's presentation about the TinyML Smart Weather Station Challenge using the Syntiant TinyML Board. So thank you for joining us. I'd like to thank the TinyML strategic partners for making these events possible, including Analog Devices, Aeon Devices, ARM, Deep Light, Edge Impulse, EMSA, PhotoHub, Greenwaves, Gravity, IBM, HotG, Imagimob, Itemus, Kilkatech, Layden AI, Microsoft, Noda AI, NXP, OctoML, Prophecy, Kixo, Qualcomm, Reality, Rexon, Renesas, SAP, Seed, SensiML, Silicon Labs, Sony Semiconductor Solutions, ST Microelectronics, Stream Analyze, Synaptics, Synsense, Syntiant, and TDK. And we will share more information about them at the end of the presentation. But I'd like to thank them all for making today possible. And looking forward to future events, on August 31st and September 1st, we'll have our first TinyML on-device learning forum. So please look at the program there and join us. It should be an excellent program. And then on September 27th, we have our first TinyML neuromorphic engineering forum, looking at the challenges there. So both should be excellent events. Please take a look at the schedules and register to join us. And then we're very excited to hold the TinyML EMEA Innovation Forum in Cyprus, October 10th to 12th. I look forward to meeting you there. If you haven't already registered, please do so today, and you'll save before the registration fees increase. In terms of the TinyML communities, please join us on the Meetup platform and the LinkedIn platform to learn more about what we're doing and connect it with the rest of the community. And then if you miss any part of today's presentation or you missed any of our prior presentations, consider subscribing to our YouTube channel where this presentation will be posted. And when you subscribe, it will notify you whenever a new presentation is added. And with that, it is my great pleasure to introduce Atul Gupta. He is the Vice President of IoT Products at Syntiant Corp. He's an expert in mixed signal microchip and system design. And prior to Syntiant, he was the President of Engineering at the High Performance Analog Division of MACOM. He has a bachelor's degree from IIT and a master's degree from the University of Calgary. And with that, I welcome Atul.
Thanks, Ira. So in this presentation, we will see how you can use Syntiant's TinyML board for the upcoming weather challenge. My contact information is here, so feel free to reach me. So I will start the presentation with recapping TinyML challenge, which is a smart weather station. And then I'll talk about the Syntiant TinyML board, what's in the board. And then I'll talk about the key technology which is behind this board and how that benefits the edge computation. And then I'll finish the talk by providing some tips how you can use a TinyML board and how you can actually set up your testing for this upcoming challenge. So in here, I'm actually showing a couple of links. You can reach out to these links to understand better what this challenge is all about. You can actually see a video as well, which talks about the pertinent, important things about this challenge. So here I'm just taking some snapshots of that presentation and trying to talk about what important things which we are talking here. So this challenge is looking for a weather station. Generally, weather station would have a rain and wind measurement. Uh, Wind measurement can easily be done with a fan attached to some kind of electronic circuitry, which would find out how many RPM it is running, and that would give you indication of the wind speed. But that would have moving parts, and in this challenge, it is expected that there would be no mechanical moving parts. And the purpose behind not having anything moving part to increase its reliability, and the whole system would cost less, and it would be easy to maintain. Of course, it has to be low power so that it can be powered by battery or small solar cells. And then it would be only communicating when some change in the event in the weather changes. So the question is that how would you measure wind or rain without having any mechanical parts? And that's kind of the gist of this challenge. So the idea here is that you can actually find some acoustic signatures which are generated by the rain and wind, and then use that signature to predict what is the rain or wind is happening around the station. Just because there is no moving parts, and it would be only listening into these signatures, it is expected that it would be rugged, it would be used with a small amount of power, and that is the kind of a gist of this competition. There are multiple prizes and awards. Syntiant is also giving some incentive and prize. So if there is an entry with the Syntiant TinyML board, we would provide $100 rebate gift card. And this is available to first 25 entries. There is also a $500 gift certificate for the best project, which is using Syntiant's TinyML board. So moving on, I'll talk a little bit more about what this board is about and how you could use this board. So when we designed this board, we kept a few things in mind. First off, most important thing is that it should be easily accessible, so people can actually get this part in any part of the world. It should have as many components as possible, so they don't need to have other components to make it work. There is no wireless connectivity on this board, but we did provide some GPIOs and even the power to a companion module. So in theory, you can use any of the module, for example, NB-IoT, Wi-Fi, LoRa, or Bluetooth. This provides about 1 watt of power. So if that works, then you don't need external power supply. But if the power requirement for the module is higher, then it can be powered up separately. We also focus to have the BOM cost of this board so that we can produce this part at very low cost. And the main technology behind this board is Syntiant's neural network technology. And it really shines is that it can provide a lot of throughput, which is for AI applications with very low power. So this board can be powered with the small batteries, and it would last very long time. It's also designed with a small footprint. The flow to use this is actually pretty easy. People can get started, and then they can actually make the first project within 2 hours. So how people can use it across the world with the zero touch, that's one of the key things behind this board. And also this board is ideal for capturing in situ data as well. So let's talk a little bit more. So we talked about that this board is available throughout the world. and it is done with a DigiKey. And as I'm showing this is snapshot that the board is available, for example, in India, and also it can be bought with the local currency, which is Indian rupees. Similarly, in other countries, it's available, and the same inventory is applied, so you don't really have shortage of the components at different countries. This board is available and with open source code, which means that there is really no need to sign any NDA, and people can get started right away when they buy this board. There's really no MOQ to buy in this board. Single one would be sufficient. And the board could also be used in your pre-production systems. And as I said earlier, that you can actually use this board as in situ as well. And this could be used for further design if you want to do cost optimization or you want to integrate with your system. So we talked about that the board should be easy to use. So when you buy the board, you can actually use our tutorial, which is on our webpage. And once you complete this tutorial, you should be able to see the board is recognizing go and stop keywords. And this tutorial is very simple to use, and it takes about 2 hours.
So a tool with, excuse me, with that the quick go and stop keyword models, is that you need to add a microphone, or what's the input mode for that tutorial?
Yeah, so it would be using microphone, but since microphone is already integrated in the board, so you don't have to do anything special. Okay. Thanks, Aaron. The tutorial is provided with for Windows users as well as Mac users. And if you want to know more about it, here is a link, and you can scroll down to see the links to the tutorials. Some more technical information is also available where you can find it on this particular link. So once you make the board work, after that, you may want to actually do different things, which means that you want to do some programming on the host side. So there is a host processor on it. And we actually used Arduino style programming, and that makes it very easy. And you can leverage rich Arduino libraries. To get started, you can actually get the source code at this particular location, which is shown here. And from there, you can actually modify the firmware and then make the board do whatever you like to do.
So just a few questions from the audience already, Atul. Does the TinyML board support any popular real-time operating system like Zephyr, Embed, and more specifically, what OS does the hardware support?
Yeah, so there is no RTOS or things like that running on the board. It is actually using very simple MCU like programming. And if you have used Arduino type board, for example, Maker 0, then you would know what it is about. So whatever you can do, let's say for Maker 0 series board, you can do the same thing on this board.
Okay, thank you.
So moving on, as I said that we made this board with the low cost, low power, and small size in mind. So the board is available for $35, but it can be further, if your application requires even lower cost, then it can be further customized, and you can take out some of the components or replace it with some lower cost. So this is a starting point, and you can design a system which may cost even less. It is lower power, So when it is in always on inference mode, it draws less than a milliamp current from the battery port. The technology, the core technology behind it actually takes even less power. It's only 140 microamp at 0.9 volt. This board is kind of optimized between cost and low power. But if the power is a key, then this can be further, the system power can further be reduced. The size of the board is also kept as small as possible. It can easily fit in, for example, Apple Watch case. And what that allows you, that you can actually have an enclosure, let's say, and you have not made your final product yet, PCB. You can use this board so that you can collect in situ data, which will take care of the chassis and the enclosure and things like that. This board actually has many components which you'd want in a system, and that's why it does not require anything else when you want to deploy it. It has a host processor, and it can communicate directly with the USB port. It has a PMIC chip. It can charge a battery, and when the power is not available, then the board can be powered from the lithium polymer battery. It has a micro SD slot, which is actually most convenient for saving data. So as you know that you can put 32 gigabyte of micro SD card, and that actually could save tons of data. It also has, as I talked about, a dedicated neural processor, which is connected to the microphone and 6-axis IMU, and that's where it would be doing the inferencing all the time at very low power. Is there any questions so far?
Yes, there's one more question. I think it's not whether you can run Linux on it, but you mentioned that you have the tutorials for Mac OS and Windows. Is there similar resources for Linux?
Yeah, so Linux could also be used. And if there's anything which doesn't work, then let us know. I'll figure it out. You can follow the tutorials, and once you follow the tutorial, it would be quite easy to figure it out how to make it run on Linux. Okay.
Okay, and then there's a question, is it possible to capture the audio on the SD card?
Yes. So the main purpose of this micro SD card is to capture the audio, and you can actually can capture continuous audio which is uncompressed directly on the micro SD card.
Okay. Thank you, Atul.
Yeah, thank you. So let's look at the block diagram of this board. So this board is built around NDP-101 chip, which is a purpose-built neural accelerator. And it is connected to a microphone and accelerometer and gyro. When you would be using in always on inferencing mode, then the rest of the system would be at sleep and only these components would be working. And that's how the power is minimized. When some significant event happens, which you're looking for, then NDP chip would wake up the host processor with the interrupt signal. When you are developing the system, your model could be downloaded through micro USB port. So the model first goes into host processor, and then it is saved in the NOR flash. And next time when you boot up, the model goes from NOR flash and goes into NDP. When you want to collect the data would be going from your microphone to NDP chip. NDP chip passes the data to host processor, and that can be saved in the micro SD card. When you want to charge the LiPo battery, you would be connecting it to micro USB. So it would be charging the external LiPo battery. And when it's not connected to the computer system or some USB power, then LiPo battery would be powering up the system. One of the unique feature we have on this board is that we generate a 5-volt signal, which is programmable, and it's using OTG functionality of the PIMIC. So that functionality would actually make one of the pin of the header as 5 volt, and it can source about 200 milliamp current. Then there are other GPIOs which could be used to toggle an actuator, or could be providing communication signals to the accompanying module for wireless. Any question on the block diagram?
Does not appear to be. So
I'll come back to it.
Oh, wait. Yeah. There's a question about what are the 3 I/O pins that you mentioned. Are you going to cover those later, or do you want to talk about those now?
So some of those I/O pins are actually documented in the tutorial. There are actually 5 general purpose I/Os and 1 special pin which provides the supply, and then you have ground and things like that. And these are simple MCUs, GPIOs, which could be used for different purposes. Okay.
Okay. Thank you.
Thank you. So now let's talk a little bit what is the core technology which is used for this board and what unique things it has to offer. So this board is built on NDP-101 chip. And inside this NDP-101 chip, the main block, or it's built around this neural network. And the implementation of this neural network is not like a MCU style, but it is done like an ASIC. And that's why it takes very low power. It also has special features for audio stream processing. For example, it has a audio front end, and then it actually extracts the feature. So all of these things are done in the hardware, and that's why it takes very low power. This chip also has a Cortex M0 processor as well, and that can be used for housekeeping and things like that. This has about 560K parameters. And when you are using with the microphone, the core takes 140 microwatt of power. And when you use with the sensors, it takes only about 100 microwatt of power. And this is always on, which means that it will be continuously processing the incoming signal.
So actually, related to that, since the microphone and the IMUs go right into the NDP-101, somebody was asking, how would you connect an external sensor, sensors other than the onboard accelerometer microphone? Do they go through the microprocessor, or do they connect directly to the NDP-101?
Yeah, so on this board, there is no connection to the external world from the NDP chip, which means that you have to use the host processor as an intermediary block, and it would be collecting the data from external sensor, and then it can feed to the neural network.
And in this configuration, that's the case, but just curious, if somebody was trying to make a more power efficient system, then they could feed it directly into the NDP-101.
Yeah, so that's true. It can be done. And probably at that time, somebody would be making a customized hardware, and then we will provide the support how to do it.
Okay. Okay, great. Thank you.
Okay. So as I mentioned before, NDP-101 is a purpose-built chip for neural computation. And we all know how compute intensive this job is. So nothing can beat this kind of a type of implementation. And this neural network is based on Syntiant's Core 1 architecture. We have done some benchmarking to see what kind of advantage it can provide to customers. So with the next best alternative, where we compared, and here is a link for that comparison, we find that it is 200 times efficient when it comes to inferencing. So this is not 1 or 2 or 10% improvement. We are talking about 200 times improvement. At the same time, this provides about 20 times more throughput. So now you can actually do more computation, and it is done at a very low power. And how it affects people is, for example, for this application, here we want to leave the weather station running in the wild, and we don't want to be going and changing the battery all the time. And this would be keep running with very low power. So that's the main purpose about this board and this technology. Is there any question on this as well?
Not on the performance. There's some other questions when we get there. So.
Okay, great. So now that we have learned what this board is about and what type of technology it is using, so let's take some time and then see how people could use this board and what kind of problems they may face and what could be the solution. So very first thing comes to my mind is that this particular chip and board is designed for more like a binary classification. So for example, you have a go and stop keywords. So you are really detecting whether go or stop is said or not. Whereas in a weather station challenge, you are expected to find what is the speed of the wind or how much rain has fallen. So one of the things which we can suggest is that you can have multiple bins. For example, you can have a wind velocity be measured at a 3 to 5 meter per second and 5 to 8 meter per second and things like that. So you can have multiple classifiers, and these classifiers would be trained for that type of wind noise which is generated or the acoustic signature which is generated. And after that, you can actually do some kind of averaging or some kind of estimation based on that.
So is there a practical limit to how many bins or classifiers somebody could be running, or what's the constraint that typically you run into?
Okay, so that's a very good question. So this chip is designed with the 64 classifiers. Generally, we don't expect people would be using all the output classifiers. And for the sake of this particular challenge, and we'll see later that how would you generate the wind? If you are using, let's say, table fan to generate it, then you can put like 3 or 4 settings on the table fan. So then you may be actually having the same number of classifiers here. But if you want more, then as I said earlier, we can go as many as 64 classifiers. Okay.
And each classifier has just it detected, not detected. There's no bins within each classifier.
That's correct.
Okay.
Okay. So the flow which we have also integrates posterior filter, and that actually analyzes multiple evaluations as the time is going. So all these inferences go in a queue, and the final decision is made based on all those activities. So if you want to disable or you want to put benign values, then here I'm suggesting you can actually put these benign values, and that would actually make the posterior filter not interfering what you want to do. And this whole flow is actually based on edge impulse flow. And over here, just before deploying, there is a small icon, which is generally hidden. It is not meant to be used. but here it could be used. So once you click on this JSON file, it would open up a window, and you can change these default values or the previously optimized values by these parameters, and then posterior filter would not be interfering with here what you want to do. So after the capturing or using the inference, the host processor can actually keep a log of these activities. They're about like a 40 inferences per second. So there's a lot of information coming, and the host processor can do some kind of averaging or accumulation what's happening, because in the end you want to say how long that type of like the wind speed has been, because over time the wind speed would be changing as well. Is there any question?
I think back in terms of the classifiers, I think somebody's questioning maybe back a slide or two that does the user have to specify the architecture, the number of neurons of fully connected layers specified, or can it be changed, or is that done automatically?
Okay, so that's a very good question. This is based on Syntiant's Core 1 technology. And the beauty of this technology is that the neural network is already fixed and you don't have to worry about it. And it is fully embedded in edge impulse flow. It has input could be as many as 2048, but typically we use 1600 inputs. Then there are 3 fixed layers with the 256 internal nodes. And then you have a 64 output classifiers. So when it comes to defining what goes in, it's actually quite simple, and you just need to follow the edge impulse flow, and how the data goes from your microphone to the neural network is all predetermined, and it's easy to use. Now this output 64 classifiers, that is selected based on how many classifiers you want. So if you want 3 classifiers, then it will only be using 3 outputs. One thing I want to remind here is that you always want to define open set, because generally people only focus on what things they want to detect, for example, go and stop. But when somebody says something else, if you don't define an open set, then it would be forced to make a decision, and it would be saying something, let's say as I say hello, and it would make it either go or stop. So if you want to make sure that it does not trigger to something random, then you could or you should define an open set, and that open set you can actually put all the other things where you want to get it triggered. So 64 includes the open set as well.
Thank you.
Okay.
So actually, here's another question about classifiers. If you're using 3 classifiers, then do we get to modify the intermediate layers? They would like to know, do they have flexibility in those? But I think you said that the model is fixed, but is there any adjustment?
The model is fixed and it is very low power. So even though theoretically one can reduce the number of internal nodes, but to make it easy, we just leave them maximum. And then when we do the training, it would be using all the neural net like parameters it has, and that would give you the best performance anyways.
Okay.
So let's talk about the low power. As I said earlier, that the board takes less than 1 milliamp of current. But generally, when you follow the edge impulse flow, which is based on our tutorial, you may not actually see that the output, the power drawn from the battery is 1 milliamp. Actually, it is a lot more. It's about like 12 milliamp. And that includes current of the LEDs, etc., which are on the board. And the main reason of this is that if you want to put in the lowest power mode, and I'm actually showing you a repository here, which is available on our forum, that would actually give you the lowest power, which is about 1 milliamp. But then it's not that easy to use for debugging and development, because it actually loses the connection because it turns off the connectivity to the USB. So when you are developing the model, it would be actually not shutting down the host processor, and most of the power is taken by the host processor. So you would be looking about 12 milliamp of this processor power. For this demo or for this challenge, we are saying that it may be good to leave that host processor running, and you may be using the averaging and things like that in the host processor. So you would be measuring about 12 milliamp current of the battery. Having said that, it is easy, or it is possible to move that functionality in the NDP chip, and that would only take a few microamps of extra current. So yes, it is possible to free up the host processor. But for this challenge, we would say that feel free to keep using the host processor because it is easy to use, and you would be using Arduino coding style. And even if you measure 12 milliamp current, we would consider it is same as 1 milliamp current, because we know that that processing could be moved in the NDP chip. So, but if when you want to really deploy and we get to that point, then we could be using a repository which is shown here, and then it can be demonstrated to take less than 1 milliamp current. Does that make sense to you, Ira?
Yes, it does.
Okay, great.
And one question that may be related to the power consumption, but it was asked earlier, but what's the maximum sampling frequency for the microphone, and is that changeable, and does that change power consumption?
Yeah, so all these things are kind of fixed. There is a way to change those ones, but that require a lot of support. So we would recommend not to change it. So by default, the microphone is sampling. It's a PDM interface. So there's a sampling happens with the PDM interface, but effectively in the end, all these things are converted into 16K sampling with a 16-bit resolution.
And then one other microphone question while we're on it is, what's the frequency response, or do you have a spec sheet for people who need those details?
We can provide what components are used and what would be the response based on the settings which we are using. But generally, it is good for speech, and that's a kind of, I think, limits. It's a 16 kilohertz sampling rate, which means that Nyquist frequency would be 8 kilohertz.
Okay, great. So anybody who needs more details on that, they should reach out to you.
That's correct. So one other challenge which I was seeing on the original description of this challenge is to measure and get the data for the wind and then correlate it to actual weather station. If you can do that's great, but if it is not feasible in a short period, especially in California, when you don't get a lot of rain, or you do get the wind, but you cannot really predict it. So for the sake of experimentation and testing, I was just thinking it would be okay to use a table fan, and then you can have multiple settings. They generally have like 3 settings, and use that to generate, to capture the data first, and then later on, using the same setup, you can actually show what kind of wind speed you are measuring. So this is a simpler and something more repeatable thing which you can do. And of course, once you get this working, you can deploy in the field and then collect more data. So as far as Syntiant price goes, it would be okay to use a table fan, and we would honor and consider those entries. So for the rain, again, I don't want to go too far in giving hints because the whole purpose of this challenge is to leverage people's creativity. But then I was still thinking that how would actually you, again, capture the data and test it? So two things I could think of is that you can use shower in the shower tub, and you would probably hear different acoustic signature, and you can actually change the flow of the shower. And as it hits the shower tub, this whole thing kind of makes a different type of sound signature, and you could be testing that. You could be using that for capturing the data and eventually for demonstrating. Another idea could be is that you can accumulate the rain and then have a system where the water actually drops, it drips drop by drop, and then you can actually count the drops. So as I said earlier, that TinyML board is designed mostly for binary kind of classification. So having something which is continuous and maybe a little bit difficult, but now here, if you can convert that flow into drops, and then if you could measure or count the number of drops, now you have converted a continuous input into a discrete input. And that discrete input is really good for this type of technology. And then it would be a lot more accurate too, because each drop would be difficult to miss. And I think that would be very accurate system. And I think how you convert these drops to make an acoustic sound, that again, I think is a challenge. And you have to get creative where it drops to, and then what kind of sound does it make. So let's talk a little bit more about the interference between the two sound signals. Wind and rain, they would produce different sound signatures, as we talked about. And it is expected that you would be testing both wind and rain simultaneously, which means that you actually have to make a comprehensive matrix, which you can do by augmenting data. So you can have the mixture of all these possible combinations. So theoretically, it is possible that you can actually detect both wind and rain. But again, for the sake of time and then how much you want to spend time and doing this thing, I would recommend that it is okay if you use two separate systems, one for the wind and one for the rain. And even if you have to use two of these boards, still it's a $70, which is less than $100, which is suggested for the challenge. So I think it would be an okay solution as well. And then you can demonstrate wind and rain simultaneously or without interfering on two. Okay, so this is my last slide. And how we are doing with the time?
Well, we're doing fine. We have a few questions after you finish this, and then we can tackle some of the questions.
Okay, great. So yeah, in this presentation, I talked about salient features of this challenge, and what things you could do and how you can use TinyML Board, and what is uniqueness about TinyML Board, and how everything can come together. If you have more questions, there is a forum, and here is a link for this forum. There's already some good material, and then if you want more, you can ask questions. And there are some people who have been collaborating on this forum, so it would be good, and feel free to collaborate with other people. So I really invite people to join this forum and then help each other out.
And then we also have the forum on forums.tinyml.org focused on the challenge too. So.
Okay, yes, very good. So we can put some links back and forth where people can leverage their findings and things like that. We also talked about in this presentation the core technology, and you can see that in this particular challenge how you can extend the battery life, and I think that would be really great. Then how you use TinyML Board, its existing hardware, software to provide a solution. And that's very doable. And feel free to reach us out. And then again, get creative to convert this rain and wind into acoustic signals and capture data and then make it a success. So this is my last slide, Ira.
Okay, thank you, Atul. So let's dig into some of the questions. Here's an easy one, I hope, is what is the weight of the board?
What is the weight of the board?
Yes.
Okay, so I don't really have any measurement, but I think it should be less than 10 grams probably, but that's what I expect.
Okay. And so there was a question whether you could run deep learning models.
Yeah, so it's a deep neural network, and it is expected that you can make a deep learning model and run on this one for inferencing.
Okay. And then is it also possible to run detection models in inference mode?
The detection in the inference mode, right?
The question is written is it possible to run detection models in inference mode?
I'm not sure. Like generally, the detection is kind of implied when you are doing the inferencing.
Right. So I think we'll just mark that off, and then okay. So let's see. Object detection. I think they'll have to follow up specifically with you on this one. Mm-hmm. And then I think you gave some hints, and I think for people who want to solve wind direction, that would be an interesting challenge, but let's let them figure out some approaches to that. So let's see, with that, are there any other questions? Okay. Well, why don't we direct the questions to the forums, and we'll take them from there. I thank you, Atul. Once again, I'd like to thank all the TinyML strategic partners. The executive strategic partners are ARM, Edge Impulse, Qualcomm, Syntiant. The Platinum strategic partners are DeepLight, Kilkatech, Reality AI, Renesas, Sony Semiconductor Solutions. Our Gold strategic partners are Analog Devices, PhotoHub, Layden AI, Microsoft, NXP, Seed Studio, SenseML, ST Microelectronics, Synaptics, SynSense, and I also would like to thank all our silver strategic partners, Aeon Devices, EMSA, Greenwaves, Gravity, HotG, ImagineMob, Itemus, Noda AI, OctoML, Prophecy, Kixo, Rexon, SAP, Silicon Labs, StreamAnalyze, TDK, and IBM. And with that, I want to thank everybody for joining us. We hope that this was informative. We hope you get excited about putting in submissions to the TinyML challenge. And thank you, Atul, and everybody have a good rest of your day. Thank you.